Good morning. I wish first of all to thank Alexander for the kind invitation. It's an honor to be here, and I wish to thank him both as a organizer of this conference and as his president. Under his presidency, we are getting better and better with this. So thank you so much for your work and for your time. And well, it's always difficult to find an interesting topic for a keynote lecture because you must be sufficiently competent and the topic should be of interest for the audience. So I hope you will find this presentation as interesting. I had also some discussion with Philippe about the problem of the interest in keynote and plenary lectures. So maybe he will give you some important details on that. Well, the topic of this presentation is the role played by the graphite nodules in ductile cast irons. Obviously, this could be only an example because maybe you could find the point of the stress in this presentation as interesting also for different materials. And well, up to the half of the last century, the only way to have malleability in a cast iron were the malleable cast irons. They are obtained by means of long and expensive heat treatments. So in 1943, during the conference, during the American Foundry Society Convention, a question was posed. I mean, if it was possible to obtain directly as cast the ductility in a cast iron. And after a few months, maybe you already know that was possible. But after a few months, they found that adding magnesium, cerium, calcium, etc., it was possible to obtain nodules instead of lamellae. Well, the behavior of these ductile cast irons is clearly connected to the nodules of these graphite elements. And well, in the last 30 years, more or less, there was a question. These nodules could be considered as something that improve the behavior of these alloys, or are simply voids, and so these alloys are porous steel or natural composites. Maybe this question is simply silly, but we will see that it's not so silly. Well, considering the graphite shape, it is evident that between lamella and nodules, nodules are better because simply considering line of tension, we have some concentration on the crack tip of graphite lamella. Instead, in graphite nodules, we have not this problem. And well, if we compare for example, the stress strain behavior, we know that lamella cast irons are worst. If we compare, for example, ferritic ductile cast iron with the pure iron, more or less the matrix is the same because in ferritic ductile cast iron, in the ferritic matrix, we have only iron, and we have these balls of graphite embedded in this matrix. We can see that the behavior improves. And well, if we compare the behavior, for example, this well, it is austenitic stainless steel, something worthy with the presentation. Anyway, we can see that the improvement of the porosity implies a decrease of the stress strain behavior. And instead, if we compare, for example, the behavior of an aluminum alloy with an increase of the carbon silicium carbide content, we can see an improvement of the stress strain curve. Obviously, other mechanical properties could decrease, so we are simply considering this mechanical property. And well, at least two different approaches try to investigate the role of these nodules. First of all, the nodules as voids. And for example, we have a paper where the role of the shape of these nodules was investigated, and they found, considering tensile test, they found that the dramatic mechanisms were different mainly according to the shape of these nodules. I mean, perfect, almost perfect nodules were always damaged by means of sort of the bonding between the matrix and the nodules. Instead, degenerated maybe is a too strong word. Anyway, not so nodulized elements were usually cracked in the middle of the nodules. By considering an approach by numerical methods, they found that the simulation of microvoids nucleation growth equations were able to predict very well the mechanical behavior, the tensile stress curve in these alloys, and also analyzing the damaging mechanism, focusing the damaging mechanism on the decohesion, it was possible to simulate the interface decohesion between matrix and nodules, finding that this was the predominant damaging mechanism. Also, the problem of the dimension of these nodules were investigated, and so large nodules were more critical. This is more or less evident. Were more critical from the point of view of the damaging in these alloys, and obviously larger nodules imply the rapid growth of voids with the decreasing of strength and elongation, and the fracture of ferritic ductile cast iron was due to the coalescence of these voids. But we have also some different results, some different approaches, and some of the authors stressed other damaging mechanisms. For example, in this case, the authors considered the different mechanisms that could be obtained in the S-cast ductile cast iron and in the heat-treated ductile cast iron. In the heat-treated cast iron, we have a supplementary shield around the previous nodule due to the diffusion of the carbon on the nodule. In this case, the authors found as the main damaging mechanism the cohesion between the matrix and the nodule as the main mechanism. And instead, in the case of the presence of this wrapped graphite around the previous nodule, a sort of internal debonding inside the matrix. Considering different metrics, in this case, for example, on a stamped ductile cast iron, some other damaging mechanisms were obtained, were found. For example, the shear ligament formation, crack deflection, crack branching during the propagation. From the point of view of the simulation, other authors, also from Cassino, found that the damaging mechanism inside the ductile cast iron should be modelized using a different sequence. I mean, a spheroid rupture followed by ductile damage in the ferritic matrix and by the spheroid matrix debonding. Also in this case, the results, the numerical results were not so bad. So it is rare that using different analysis of the damaging mechanism, the numerical approach were always able to simulate the process. This paper is instead focused on the role played by the testing temperature, and the authors found that below more or less 500 centigrade degrees, the main mechanism, the main damaging mechanism were due to the nodule plastic deformation, followed by crack inside the nodules and by a sort of onion-like mechanism inside these nodules. Instead, at high temperature, the ductile deformation of the matrix implied the bond between the nodule and the matrix as the main damaging mechanism. Well, but these nodules are simply poles of graphite, or do they have an internal substructure? In this case, we can find that from the first idea of a sort of homogeneous ball graphite, balls of graphite, some substructure was found. First of all, maybe you remember I talked about the wrapped graphite around the previous nodule in the heat-treated graphite ductile cast iron. Some others found a first substructure done by a sort of shield around the nodule, also in case of ductile cast iron without heat treatments. In other papers, the authors focused their attention of the nucleation at the event, and they found that the nucleus were nucleated and it grew around some oxide sulfides, and so the internal mechanical properties could be different from the mechanical properties of the shield around this nucleus. Other authors found that the substructure depended on the sequence during the solidification and the cooling process. I mean, you have the solidification directly from the melt, then the eutectic solidification, then the cooling process, where the solubility of the carbon in austenite decreases. And as you can see in the figure on the left, these three stages are quite evident. Other authors proposed different models for the growth of these nodules, find that this structure could be quite more complicated. Maybe I think the different nucleation growth of these nodules could be also connected to the different methods they could obtain modifying the chemical composition of the ductile cast iron. Recently, we have also this nice tomographies where they found that in the nodules, the substrate is still more complicated. I mean, we have a nucleus in the center that is more or less rich of voids, and then the outer shield has some ion channels mainly due to the eutectic solidification. And so the structure of these nodules is clearly very far from simply hollow graphite. Well, the UNICAS contribution to the discussion, we worked on this topic for the last 20 years. First of all, we proposed this sequence in the solidification and the presence of the structure already 15 years ago, where we proposed that simply consider this phase diagram. It is a phase diagram for a ductile cast iron with 0.54% of silicium. We can see that being ferritic ductile cast iron in a hypereutectic alloy, we can have the direct solidification of the graphite, then the eutectic solidification, then after the eutectic temperature, a decrease of the carbonate content in austenite. And we can see that simply preparing metabographically our ductile cast irons, we found that the wear resistance of this node were different between the center and the outer shield. Here you can see a 3D reconstruction on the right, a 3D reconstruction of the surface simply after a metallographic preparation, and you can see the profile of this nodule. And we can find that the center of the nodule is characterized by a lower wearing resistance. Also performing a 3D reconstruction in the customized image processing process, we found that this center were characterized by a lower wearing resistance. And performing some minor indentation test, this idea was confirmed because we found that in the center, as you remember in the 3D tomography, there were more voids, so it's not that the hardness was lower. We can find a lower value of the hardness. And also considering the SEM ADX map, we can find the ion channel inside our graphite nodules. And it is quite nice in this figure because it is evident that it is mainly in the eutectic stage. Well, the difficulty when you do this experimental activity is that you must be sure that you cut in the center your nodule. So you are not able to find always these results because the probability to cut exactly in the middle of the nodule is not. So usually you cut the top or the bottom. It is more simple. And we also performed some tensile tests using tensile holder with a micro tensile machine. And we use this small holder to perform some step-by-step tensile test inside a scanning electron microscope and using a different microstructure, starting from a fully ferritic microstructure up to the fully ferritic. And we found some interesting results. Here you can see some steps of this tensile testing, in this case for a very nice nodule. And we found that I will not show you all the figures, but in 100% ferritic matrix, the onion light, we call that in this way, the onion-like damage mechanism was the most frequent one. And we found also some radial and transversal cracks that nucleated and propagated inside the nodules, maybe depending from the presence of more important nucleation sites, I mean, ammonium sulfide or calcium sulfide. And the debonding, the interfunctional microcracks between the graphite elements and the matrix was only seldom observed. Modifying the volume fraction of ferrite and perlite, we can see different importance of the different damaging mechanism. And for example, in this case, we have a 50-50%, maybe from the point of view of the mechanical properties, the most interesting one. And it is also interesting that from the point of view of the metallurgical approach, because in this case, for the S-cast alloy, we have a graphite nodule, a shield of ferrite outside the nodule, and then a matrix of perlite. So it's very interesting for a metallurgist. And we can see that we have the debonding, we have the internal onion-like mechanism, and we can also observe some internal cracks, usually corresponding to the nucleation sites. Here, for example, you can see the debonding between the layers, that is quite evident in this case, and the initiation and propagation of cracks in the matrix, starting more or less from the equator of the nodules, propagating the ferritic shield with the perlite that is still quite undamaged. The 100% of the perlite still show different microstructure, morphology of the damage. As we can see here, for example, an important presence of the nodule debonding, or the internal debonding between the different shield, or the crack corresponding to the nucleation site. Now we have some reconstructed step-by-step videos where we can, where we can see, for example, the increase of the damage, in this case, after the yielding point, as a ductile crack initiation growth, firstly in the middle of the nodule and then in the outer shield. In this case, always this is the 100% of the right. In this case, we have the damage already in the last stage, as the bonding between the matrix and the nodules, and the nodule. In this case, always 100% of perlite. Maybe in this case, we didn't cut exactly in the middle, but anyway, we have this internal bonding between the core and the outer shield. And in this case, if I correctly remember, it should be an internal crack that initiated just before the yield strength, the yield point, and propagated inside. Well, this is a more or less an overview of the damaging mechanism we observed, and the role of the nodules depends on the matrix. So this is also an important point that should be stressed. Well, so in conclusion, according to my presentation, our results, and also according to the papers presented the last 30 years, maybe it is not a silly question to ask if ductile cast irons are porous steel or natural composites, and maybe some possibility to improve their mechanical properties could be obtained trying to improve the nucleation and growth of these graphite nodules in order to modify the damaging mechanism of these alloys. Thank you.